Good morning, by which I mean afternoon. Fancy meat computers. How's everybody doing today? I hope that you're doing okay. I hope that today is a day that is okay. Okay today. Hello, it's 2 people watching. Holy smoke. Am I on the right stream? This is the right stream, right? Yeah, this is the right stream. I would appreciate it if some of y'all could say something so I know I'm not, like, just speaking to the wind. Yeah, okay. Checking the announcements. Checking the announcements. Checking. There is a midterm today. Ah, there we go. That explains it. Which midterm? Oh wait, that's tomorrow. Yeah. Boo-hoo-hoo. Nobody takes my class seriously. Oh, 3DS3? Yeah. Great. Well, at least we have 4 people. 4 individual entities in the chat. That'll have to do. Yep. Yeah, I have heard that it's a busy week for you guys, so... Yep. Speaking of hearing that it's going to be a busy weekend for you guys, a bunch of you begged for mercy over the Piazza channels yesterday, begging for an extension on Project 2, and I, in my beneficence, as your Lord and Master of Programming Languages, I have decreed that mercy shall be afforded to the poor subjects of my realm. I'm giving you guys a 2-day extension on the Project 2 deadline, and that should be enough, so stop asking for extensions. Please stop asking for extensions. Anyway, so, good. Don't forget my message on Assignment 6, Question 2. Yes. So, Mark wanted me to talk about Question 2 on Assignment 6 very briefly. I will talk about it briefly because it is a brief question. So, Question 2. Prove that every subterm of a well-typed term is also well-typed. So, the first thing that we have to do is to establish what we mean by something being well-typed. And our traditional definition for well-typedness is that there is some rule of typing which must apply. Ordinarily, we indicate that a rule of typing applies without specifying that rule of typing by using the :t operation to indicate a relation between the term and the typing and the set of types. So essentially, you are being asked to demonstrate that every subterm of a well-typed term also has a typing relationship applied to it. If you throw the base cases in too, then you could do induction over typing derivations in order to accomplish this task. Someone thought that there was a midterm today, which, you know, people do occasionally forget they have tests. But yeah. So, so that being that, let's move on to this. So last time we were talking about typing and typing contexts and why typing contexts are mandatory for lambda calculus and what we can do to provide typing contexts. Remember our example, right? Which motivates why we need typing contexts. So if you have a lambda, right, that gives a type to an abstracted variable, it is entirely probable that that abstracted variable is going to be used later on to determine typing relationships. In this example, we're assuming that S2 and S3 have the same type. So in order to have a typing rule that types this conditional statement, we need to know if X is a Boolean or not. Now, if you look just at this term itself, there's nothing about it to suggest that X would be a Boolean. That is to say, if X were a free variable and there was no abstraction here, this would be an untypable expression. But since we know that X is a Boolean from the lambda expression that wraps this term, we can say with certainty that X is of type Boolean, which means that this expression is typable, which is a very important result. And you can imagine, if you had several lambdas going on here, right, you would have to be able to pick out the type of X from among a selection of types, all provided by lambda abstractions. Basically, you have a set of typing rules, right, which grows by 1 every time you pass through a lambda, right? So, the way that we write this is we use the turnstile character. So we specify a typing context. A typing context is a set of typing relations. So it's a set of mappings from the domain of terms to the domain of types. So that's the context. We then have a term that produces some type. So really, with respect to the way we used to do things, this is the new part, right? We now have the fact that certain typing relations can aid us in establishing the typedness of a particular term. So, in general, we will often need to keep track of multiple context variables because lambda calculus has to manage arbitrarily nested abstractions. This means that the context we talked about in the previous slide was actually a set of variable typings and is a subset of all possible variable typings. For example, we might have W typed as T1, X typed as T2, Y typed as T3, and that might all contribute to our knowledge that Z is typed T4. We generalize this form to gamma proves T has type T, where gamma is the set of variable type relations. This is gamma! Huzzah! We have a brand new Greek letter. Although, now that I think about it, there's no such thing as a brand new ancient Greek letter, is there? That's a contradiction in terms. But gamma, it's alpha, beta, gamma, delta. So it's the third letter of the Greek alphabet, uppercase. This is often called either the typing context or the typing environment. More formally, gamma can be expressed as follows. Gamma is either the empty set or some gamma, comma, X typed T. That is to say, the typing context is either empty or composed by adding one piece of typing information to another context. I finally got LaTeX characters back, but I hate how I do it. Either way, I can type lambda and gamma again. Oh, you have a way of, like, you got shortcuts for that? I've just been typing it out each time. Technically speaking, I could just put, like, I could download a Greek keyboard and just, you know, put stickers on the keyboard to say where lambda and gamma are, and that would work. So the comma here is like a concatenation operator. We use it to add pairs to our typing context gamma. So because this is formal logic, we're going to be pretty rigorous about the manner in which we are allowed to speak about gamma and, like, how things get added to gamma and what order they get added in and all of that jazz. And generally speaking, it's called compose in Linux. You can enable it and then do multi-key bindings. Ooh. This is like a list in Haskell. Yes, it's like a list, except in Haskell, you put the stuff at the beginning and then you have the rest of the list. So this is like head recursion rather than tail recursion. But yeah. Alt-GL becomes lambda. Ooh. I'm going to have to look that up. Compose. Very cool. So, where were we? Yes. Yeah, so this is very similar to how lists work in Haskell. It's like a cons operator. Yeah. If we are working with an empty context, we will often find that the turnstile character has been omitted. Sorry. Strike that, reverse it. We keep the turnstile character and we omit gamma. So rather than, like, having the null character or the null set character included here, we just say turnstile and then the type. This is to say that this typing holds in an empty typing context. Yeah. The following means in the absence of any other typing information, T1 is typed type 1. So, function typing, but properly this time. Using this information, we can refactor our typing rule for lambda abstractions. So, taking into account all of the things that we now know about gammas, we can say the following. If gamma proves that this lambda abstracted term sorry, I should back up. In order to prove that gamma plus this lambda term yields the type T1 to T2, we must first establish that gamma concatenated with the typing information provided by the lambda means that we have T2, the inner term, typed T2. This is our requirement. We're gathering the T1 information from the type of X itself. We're gathering the type T2 from essentially trying to apply a typing rule to T2 with X having type T1 added to our context. In human speak, given a lambda abstraction, lambda x, which has type 1 T2, term 2, a typing context and a typing context gamma, if we conclude that T2 has type 2 from both gamma and the typing information provided by X, we can also conclude that the type of the abstraction is T1 yields T2. Very good. Still following. Hopefully this makes more sense now that we've, you know, we're talking about it for the second time. Cool. Things of note. The way this is formulated, if we begin with an empty gamma and try to type in nested lambda abstractions, we get a new typing assumption. We add a new typing assumption to gamma for each lambda deep we are in the derivation. That is a terrible sentence, and I apologize. Consider the following example. Lambda x, bool y, lambda x type bool, lambda y type bool, lambda z type bool, y. So this is how we use gammas, right? First, we have this guy. This is our original expression. We assume the inner term with some gamma, right? Gamma 1. We then assume the inner term again with some gamma, gamma 2, and then we assume some inner term again with gamma 3. The gammas, I didn't have space for it all on one slide, so the first gamma contains only the typing information for x, because that is, you know, we can pull that in as an assumption, right? We're trying to assume something that makes us capable of using our typing rules, particularly t-abs. So once you get to the second layer, your gamma now contains x and y. Third, we can pull the typing information from z into gamma. Z has type bool in gamma 3, and because we're trying to find the type of y, we can state with certainty, because y is directly in gamma 3, that gamma 3 demonstrates that y is of type bool. This is a typing rule that we haven't talked about yet. So from there, we know that lambda z of type bool.y has type bool because of we can use the typing rule for abstractions on this guy, right? Then we can again follow that process through, typing abstraction, the abstraction typing rule on 6 and then on 7 to derive the fact that this entire expression Actually, I made a mistake. I should have had included arrows there. Drat. Sorry about that, guys. Maybe I can just fix it quickly. So, this is an abstraction. So the first layer is y might be typed bool, but we have to introduce the typing arrows now. Bool to bool, bool to bool to bool, and then bool to bool to bool to bool, since these are unapplied lambdas. There we go. Ta-da! We lose our, oh, that's too long to include that. Ugh. Well, at any rate, there you go. So, you may have noticed in the previous derivation, we used a rule that we haven't defined yet. This is the typing rule for variables. In order to demonstrate that gamma shows that x has type t, you must have x showing type t as an element of gamma. Ever read a word so many times that it doesn't look like it's a word anymore? Oh, all the time. All the time. This rule simply states that if a variable has a type association in gamma, we can pull that type out of gamma and type the variable with it. In order for this to work, however, we can't have duplicated variable names in gamma. So this is an important point about gamma, right? If you have, you know, lambda x, lambda x, lambda x, you know, you can't add multiple x's into gamma. Essentially, that's bool with you right now? Yeah. Essentially, if you have, like, say you had x at one layer typed bool, and then at another layer you had it typed natural. And I know we haven't got naturals at the moment, but just use your imagination, right? If you put both of those into your typing context, which one do you pull out when you need to know the type of x? The answer is, you've got a conflict. So, the way that we avoid conflicts with these, which can be thought of similarly to the idea of capturing substituted variables, is we're going to use the same meta rule that we used to avoid capturing, as I said, avoid capturing variables. If adding a variable to your typing context conflicts with an existing name in the typing context, you need to perform a relabeling over that lambda in order to fix it so that there's no longer a conflict in gamma. Fortunately, it is true that as long the two expressions in lambda calculus are completely equivalent under consistent variable relabeling. So, you know, it's still the same expression. You've just made it, relabeled it so there's no conflict. Yes, we can use the same meta rule that we used while describing substitution semantics. If a conflict occurs, we relabel the term with a non-conflicting variable name. Ta-da! Submit your application. Ha. Application. That's the pun, because we're talking about application. To round off our terms in pure lambda calculus, let's address function application. So, remember application, T2 applies to T1, right? In order to demonstrate that this application has type T2 from some context gamma, we have to prove that A, given that same gamma, T1 has type T1 to T2, and that T2 has type T1 from that same set of assumptions, or that same set of typing contexts. Now, bear in mind here that just because of the way lambda calculus works, we are expecting T1 to be a function, right? If it's not a function, then it wouldn't have this type. So we're expecting T1 to be a function, but the typing information that's provided to it is only available in the subterm of the lambda, not in T2. So T2 has to be provable. It has to have a type. It has to be typed based on only that information which currently exists in gamma. Excuse me, we can't borrow information from T1 and feed it into T2, because that would violate our rules with respect to what is a bound and free variable. Simply stated, if T1 evaluates to a function mapping a term typed as T1 to a term type of T2, and the term provided as an argument has a type T1, we may conclude that the application of T2 to T1 has type. These typing rules are summarized in the following chart. You'll notice that in the textbook they use like T11 and T12 for some odd reason. I simplified it to T1 and 2, but you know, that's useful in proofs that are going to be coming up later on. So there's actually a problem with this. Without looking ahead in the slides, all of you people who I know look ahead in the slides, if you have looked ahead in the slides, you're not allowed to answer this question. But there's a problem with this typing system. What is it? Another way to say this typing system is currently degenerate. There's no well-formed type that is possible in just what you see on this page. And notice, the things that are included on this page are just the typing rules for, just the typing and evaluation rules for the pure lambda calculus. We do not have the Booleans included here. So without Booleans, this doesn't work. Why? There's no well-typed term in this language, as it currently sits. There are no base cases. There are no base cases of what? You have to be more specific. We use infinite recursion on the left side. Where? There we go. So we have defined t as a thing that maps a t to another t, but if all t's are only t's that map are only mappings from t to another t, then there's nothing at the bottom, right? We need the Boolean type in order to have some type that doesn't require a further definition of type in order to exist, which is why this is, as your colleague states, an infinite recursion. Things of note. In the foregoing slide, the highlighted parts are things that have been added relative to our operational semantics of pure untyped lambda calculus. Fun fact. The pure system is actually degenerate. Not in the internet sense of the word degenerate either. Or in the Letterkenny sense. This means that there is no valid well-typed term in the calculus. There are no valid well-typed terms. The reason is the way that we are defining types themselves. We've recursively defined t, but no base case has been provided. This is why our examples so far have included the Booleans. Is anybody besides Mark still alive in the chat? Awesome. Well, we admire your efforts, Mark. We admire your efforts. So bool will be the only base case of t. For the time being, yes. You know, obviously, we're keeping things simple for the moment. We don't want to have to worry about, like, predecessor and successor at the moment. It's sufficient. Like, right now we're examining how to type lambda calculus. It's not difficult to smuck those two things together, you know, post-fact, right? So yeah, we do need some base case, so Booleans are convenient for that purpose. But, you know, eventually, once we start integrating the natural numbers, you'll see nat coming up as a type that we can have in the set of types as well. And of course, you know, if you apply this to real programming languages, you would have, you know, Booleans, integers, characters, floats, all of your standard cadre of types that you would use. So yeah. But yeah, for the time being, floats are sufficient. So, we're going to now talk about some of the properties of typed lambda calculus, but we're going to have to set up a few of the same types of lemmas before we do that we did back for UAE. This should seem relatively familiar. As with typed arithmetic expressions, it would be useful to be able to derive the types of the subterms of TLC from the typing information of the superterm. We will therefore introduce lemma, inversion of the typing relation. So, if we have gamma proving that x has type R, then we can conclude that x having type R is an element of gamma. Very simple, right? Sometimes in math, it's necessary to prove obvious things, or state obvious things, because sometimes obvious things aren't that obvious. For I abs, if we have some lambda expression which has type R, then we know there exists an R2 such that R is equal to type 1, and type 1, sorry, R is equal to type 1 becomes R2, and that gamma plus x typed as type 1 proves that T2 has that type R2. So we know there exists some R2 such that the inner term has that type, and that the lambda as a whole is a function from T1 to R2. So there you go. We can conclude that. Oh, I've repeated that on 2 slides. Oops. So, furthermore, if we have typing information for T1, T2, I thought I had proofread these. I'm sorry about this. T1, T2 should have type wait. There it is. T1 to T2 should have type T12, I think, according to the... Let me just take a look in the textbook for a moment. Inversion lemma R. Okay, so if that has type R, there we go. I suppose that makes sense. That's consistent with the rest of it. There we go. So, if we have a function application which has some type R that's well typed, then we know there must be some T11 that exists such that T1 has that type given the typing context, and that T1 has the type T11 to R, and that T2 has that same type T11. And our inversion rules for the Boolean operators are precisely as they were under untyped arithmetic expressions. So, although we have chosen the path of explicit typing for TLC, so far we have only explicitly typed typing typed variables. So far we have only explicitly typed variables in function abstractions. It remains to be shown that this is sufficient to make the whole system typable. One property that helps convince us of this fact is the property of uniqueness. Uniqueness is kind of like determinacy with respect to typing relations. Remember, determinacy in evaluation meant that any particular term only evaluates to one additional term, right? You can't have something evaluate twice. Is IF missing a type? Yeah, it is also, isn't it? Jesus Christ. R. Yeah. This is what I get for copying it out by hand, eh? Sorry, guys, it's been a long week. It's been a long couple of weeks, actually. So, I'll upload this once I'm finished with it. Right. So, theorem, uniqueness of types. In a given typing context, gamma, if all free variables of a term t are in the domain of gamma, then t has at most one type. So, that is to say, if we have a situation where all of the free variables have some type that's represented by gamma, then, there's nothing left in there that could mess up our typing relation, unless we have, unless we have a situation with, like, conditional where T2 and T3 are of different types, in which case you have no typing relation applicable. That's why we say at most one type, because that includes the case where it's untypable for other reasons. But you can't have a term that has more than one type, and that's a very important property. Another way of stating this is that if a term is typable, its type is unique. Furthermore, there is only one derivation of this typing, which can be built from our typing relations inference rules. Proof sketch. We essentially have to prove that not more than one typing rule can apply to any particular term at the same time. The observation that each typing rule applies to a maximum of one term of the language is actually sufficient to demonstrate this property. For example, tapp only applies to the terms of the form t, t2, etc. That is to say, we only have one typing rule for each term, right? So, if a term is of any particular form, there is always at most one typing rule that applies to it, because there's always at most one typing rule per term. This seems simple enough, but without this, nothing else works. So, good. Similarly to typed arithmetic expressions, it will be useful to have canonical forms to refer to. So, lemma, canonical forms. If v is a value of type bool, then v is either true or false, and if v is a value of type t1 begets t2, then v is a lambda abstraction. Proof sketch. This proof would proceed in the exact same manner as the canonical forms of TAE. That is, demonstrate the exclusivity of both categories with respect to given values. How we doing? How we doing, folks? Nobody's asking very many questions. Um, like, do you have a question about the material, or is this just like a general feeling of not being up for it today? Oh, the yeses are winning. Got lost at inversion rules. Okay. So it's important to have inversion rules because these typing rules only apply in one direction without a little bit of coercion, right? So the thing, can't stop thinking about FreeSD3. Frigging FreeSD3 invading the brain space of my students while they're in my lecture. Come on, man. Like, ugh. IVAR is simple enough, but past that it's a blank. Well, let's go over it again, because it's important to know, right? So, the thing about these proofs that we are doing is that we're trying to use as rigorous and formal a reasoning as we can. I know not formal in the Dr. Farmer sense. So, in order to go from the premise to the conclusion here, right, you need to have the premise, and then you can derive the conclusion, and that rule has, that has a name. And we can say this unidirectional relationship is indicated by the name T-abs, for example. Yeah. I'm sorry, but 3SD3 and 3DB3 caused some massive burnout, and we have no time to recharge because there's work due every week. Well, I mean, I have consciously tried to cut down on, like, the workload for this class, Yeah, so inversion, as Mark states, for IAP, if you have apply T1, T2, and you know that T1 is a function from A to B, then you know T2 is a type A. The entire thing is type B. Yeah, so essentially, you can say, like, from the idea that, a term is well-typed, you can derive that it must be well-typed because you applied a typing rule to get there. And if you applied a typing rule to get there, you can assume the premises of that typing rule. So for application, for instance, if we know that T1, T2 has type T12, then we know that the two premises above here must hold. We know that T1 must have type T11 to T12, and that T2 has type T11. We must know these. And that's simply what the inversion rules are telling us here. They're very immediate. We don't bother proving them because all we have to do is like take the inference rule and flip it around, and that's how you get it. Yeah, I had a question about that. I understand both premises, but then in the inference, why is it that the type of the full statement is type B and not A becomes B? Because, okay, good question. So for the simple answer is because it's not a function. It's a function application, right? So think about the ID function, right? Let's say T1 is the ID function, so lambda x dot x, and that T2 is some y, right? When you actually make that application and you simplify it, the type of the resulting expression is going to be whatever the type of y is, right? Not what the type of the thing before. So it's like, yeah, this is you apply an argument, and that removes the leftmost term in the arrow chain. That's another way of thinking about it. So yeah, hopefully that makes it a little clearer. I'm thinking we might just leave the rest of this for another day, since, like, everybody is totally washed out anyways. Maybe things will look a bit clearer on Friday. So for a function application, the type will basically be the type of the final result. Yes! Correct. That's the whole point. Right? That's what we want to know. We want to know what the type of the thing is after it's been evaluated. Right? That's the whole point of, like, the typing system in general, is we're trying to determine what the type of an element is going. We're trying to determine what the type of a calculation is going to be before we have to explicitly execute it, using, like, this slightly weird parallel way of evaluating things where we don't actually have to evaluate things. Mark says, think of it like in Haskell, you define the function, but when you call it, you only get one return value. Yes. Yeah. So, you know, if you have a Haskell function, right, from bool to bool to bool, if you apply, like, func true, what you get as a consequence of that is a function from bool to bool, right? You apply one argument and you get a function back that requires one less argument. But I kind of feel like this class is really just teaching you Haskell. Like, if this were in Haskell syntax, I could claim this was a Haskell course. Yeah. I don't know. Would anybody be mad with me if I called class 4 minutes early? I don't think anyone would ever be mad at that. Yeah. The hardest part is that the textbook uses new operators that just means things we already know. It means things you already know somewhat more mathematically rigorously than you previously knew them. Like, this is what we're trying to do. We're trying to formalize your existing knowledge about type systems, because hopefully you've heard of a type system before. Like how it uses comma for set concatenation, even though we have two operators for that already. Don't even get me started, man. But it's because we're using the turnstile. It's supposed to look like sequent calculus, right? So the type of T2 does not matter. Only the type of T1 matters because the type is going from A to B. Well, no. Because type 2 has to have whatever the type of the first type in T1 to T2 is, right? Yeah. Otherwise, it's not typable. It's like, if you have a function that expects a... If you have a function that expects a nat, and it gets a bool, that's an ill-typed expression. Right? That's not a well-typed expression. So we wouldn't have a typing rule that would classify it as a well-typed expression, because it's not one. Are there any more questions? Yeah, it's tricky, right? Each one of these rules has basically its own naming convention. Mm-hmm. An important and interesting thing to remember about lambda calculus is that although we have typing expressions or typing rules for each of these three different types of terms, the only term that we have any evaluation rules for is application, which is why that's why lambdas are values. Okay, well, so it goes. Go get some sleep or whatever it is that you need in order to, you know, call to your mind enough mental energy to be able to continue on with the semester. Go hit a save point. Stay at the inn, get your HP and MP restored, please. If everybody could please stay at an inn before before coming to class next time, so that your HP and MP are restored, I would really appreciate it. That'd be awesome. And no, I'm not going to give you the gold for it. Take her easy, folks.